Welcome everyone to this Sussex Universe lecture. Tonight we have Professor Kathy Romer, who's going to talk to us about dark energy and how it's going to tear the universe apart.
Good evening everyone, my name is Kathy Romer and I'm from the University of Sussex. I want to thank Will and Steve for inviting me, and especially to Will for figuring out my Panopto recording problems over the last few hours. I also want to say thank you to the previous organisers of Sussex Universe Lecture Series, Daniel Haggas and Jesse Hislop, without whose legacy input we wouldn't be meeting today in such unusual circumstances. If you're wondering about the image you're seeing, this is a picture that combines the Brighton Pavilion, the Royal Palace, with a picture of the Brighton Dome. I mean, not the Brighton Dome, the CTIO Blanco Dome, which houses the Dark Energy Survey camera, and I'll be talking about that more in this talk. On the left, you can see a condor flying over the CTIO Dome, the Blanco Dome, and on the right, you can see seagulls flying over the Brighton Pavilion. And this print is available. It was designed by an excellent local artist, Michelle Dawson. Okay, you're now going to be seeing a movie which is generated in a supercomputer by the Illustrious collaboration, and it's showing you how the universe starts off dark and not very interesting, and evolves over the course of 14 billion years since the Big Bang to develop all sorts of beautiful structures like stars, galaxies, clusters of galaxies that we see in the universe today. And while that's going on in the background, I'll just give you a very quick description of who I am. I'm an astrophysicist at the University of Sussex. I grew up in Northumberland, southeast Northumberland, in a little village by the sea, just north of Whitley Bay. I now live in Worthing, which is a small town on the southeast coast. After I did my A-levels, I went to Manchester University to study physics with astrophysics. After that, I went on to Edinburgh University to study for my PhD. And following that, I had postdocs at Northwestern University, which is near Chicago, and Carnegie Mellon University, which is in Pittsburgh. And I stayed on at Carnegie Mellon, eventually becoming a tenure-track professor. My kids were born in Pittsburgh, and after they were born, it seemed like the right time to come back to the UK, and I've been at the University of Sussex since 2004. That trajectory might seem very planned out and sensible, but I can assure you that it was pretty much a roller coaster and a random walk, and I feel very, very lucky that I've ended up with a permanent job in a field of study that I absolutely love. Okay, so you can see now in this movie, you can see different structures. This simulation is now showing you the results of stars forming, stars exploding, etc. But we're going to move away from that and just go back to our main topic, which was, will dark energy destroy the universe? And for that, I'll cover 4 points. First of all, dark energy, what is it and what's its destructive potential? What is the evidence for dark energy so far? What's the evidence that we'll have in the near future? And for those of you who like to think about conspiracy theories, thinking about perhaps there's another explanation for some of the observations we've been seeing. The second part, the evidence so far, is the longest, and the last two are very quick. So don't worry if you feel like you're going to be here forever. We should still be finished in time for the clap for carers. Okay, so dark energy and its destructive potential. I think I'd like to address this as a fairy tale, and downloaded this little image from the web about fairy tales are more than true, not just because they tell us that dragons exist, but they could tell us that dragons cannot be beaten. So let's start with our fairy tale in some really useful, trademark, boxes. If the universe is one of these boxes and growing with size with time, in the very, very early universe, that little box on the far left, it would have been packed full with stuff. Now the stuff that you can see, normally I'd have this in my hand so you could, it would be easier to explain, but I'll have to do it from the photos. what we've got are 9 fluffy green balls and 1 orange ball. Those are the constitution of the matter in the universe. It's formed very, very early on, fraction of a second in the universe. The orange one is the normal stuff in the universe, the electrons, the neutrons, the electrons. And the green stuff is what we call dark matter. So there's 9 times as much dark matter in the universe as there's normal matter, orange stuff. In that little box on the left, I've shoved those 10 balls in, and there's a little bulb shining. And in fact, if I pop the top on, we'd find that all of that stuff was so compacted in that light wouldn't even shine through. So in the very early universe, it's so hot and dense that even light can't escape. It bounces around like photons do in the centre of our sun. And then the universe expands into the second box, and into that second box we've got an extra black pom-pom, but we don't have any more of the greens, we don't have many more of the oranges. Already the density's dropped enough that the light would travel through it from that little bulb. We move forward into a time about 6 billion years after the Big Bang, where we've now got as much of the black stuff, 10 black balls, as we did of the green and the orange. And at that point, we've got the densities going down, but we're not making any more dark matter, we're not making any more baryons. And then into the next box, by this point, there is 3 times as much of the black stuff, which, if you've not guessed yet, that's what's denoting the dark energy, as there would be of the green and the orange. So what's happening is the universe is getting larger, and as the universe is getting larger, the amount of green and orange is getting more and more dilute, and yet we're getting more and more of the black stuff. And the logical conclusion of that is in the future, we'll get a very large box full of lots and lots of black balls. The green and orange balls are still in there, it's just they've become very much diluted. And so you can think of it like, again, a fairy tale, magic porridge pot. We are producing more and more volume in the universe, and the more volume in the universe we have, the more of this dark energy we have. And that is why we have the title of the talk being, Will Dark Energies Destroy the Universe? And in fact, when we produce the results of the Dark Energy Survey, this rather amusing headline was popped up saying the terrifying dark universe discovered within our own universe, and it spells doom for humanity. There's many things wrong with that title, but let's focus on the word doom. If we have this magic porridge pot situation of dark energy, yes, the universe would pretty much, it wouldn't be destroyed, it just gets larger and larger and larger. The problem is, it's those green and orange balls that get further and further apart, to the point where the stars and galaxies would start sort of like being teased out, and ultimately planets would be teased away from their host stars, and even to the point where actually the expansion would overcome the forces, the microscopic forces, and pull apart particles. So that's not a good thought. So that's its destructive potential. And so we've talked about this magic porridge pot analogy, but actually, because of the unfortunate situation we find ourselves in the world, I can actually use what we would term as a technical term when we're giving talks, that dark energy is destructive because it drives an exponential expansion. Given public talks for many years, and I've always avoided that term, but now you all know what it means. So if you think about what you've been learning from the news, or maybe from Julia's talk 2 weeks ago on this Sussex Universe series, and I highly recommend it if you haven't listened to it yet. If you think about exponential growth when you're talking about infections, if you have a positive R number, and here the R number is 2, where one person's infecting 2 people, those 2 people then infect 4, those 4 then infect 8, etc., and that's an exponential growth. And you'll have seen curves like this probably in the news, where the number of infections rises up and then goes down. The exponential growth is this bit circled here in red. But the reason it comes down is because the number of susceptible people goes down, because Once people have had it once, fingers crossed, they'll be immune and they won't get it again. And so the number of recovered people goes up and the total number of infections goes down. And so you can think of there's a push up in infections when the R number is greater than 1 and a pull down as the herd immunity increases. And the analogy in cosmology is that dark matter pulls the galaxies together and dark energy pushes them apart. And thank you to my former student and friend Julian for this little graphics that's showing dark matter as a spring and dark energy as some helium balloons. And so here we've got a bit of a balance where dark matter and dark energy are pretty much the same. In this case, we've got too much dark matter, and in fact the universe collapses so quickly that there's another big bang, but this time it's a big crunch as the universe collapses back into a singularity. And if dark energy wins, it's still doom, but it's a different type. And as I mentioned before, it's all of the objects in the universe, the stars, first of all the galaxies, then the stars, then the planets in the solar system, and then the individual particles are getting pulled apart. So it's a different type of doom. It's a black cold doom rather than a hot explosive one. Okay, so we've covered a little bit about dark energy and its destructive potential. But just before I leave that and move on to the next part of the talk, I just wanted to mention that there's a few things that you might well be wondering by this point, and hopefully will be explained in the next bit. That is, how do we know the universe is expanding at all? Why do we think it's expanding in this exponential way? And quite often, members of the public get confused because they think if the whole universe is expanding, that means we're expanding too. I'm sure, like me, during lockdown, you're eating lots of cakes and biscuits, so you are expanding, but not at the same rate as the universe. On the top, those hopefully will be covered in the next part of the talk, but also during the question and answer session that will follow the talk on Zoom, you might want to ask if the universe is expanding, what's it expanding into? I've mentioned dark matter, I've mentioned dark energy, I haven't really explained the difference between them. The dark matter has the pull and dark energy has the push. Talked over that video at the beginning, haven't really explained what the relevance of that is. You might want to, hopefully that will come up later on, but if not, you might want to come back to that. Lovely question I got from some school kids when I gave a talk. If gravity is getting weaker, are the planets in the solar system changing their orbits? Okay, so next part of the talk, evidence so far, and this is the longest part of the talk, and the next two bits are very short, so don't worry if it feels like it's going on and on. Evidence so far. All right, so I'm going to break this into 2 bullet points, and then I'm going to break those bullet points down and down and down, and hopefully I won't lose you. Okay, so the 2 bullet points are: supernovae in distant galaxies are fainter than they would be if the expansion was not growing exponentially. Remember, the exponential is like having an R number greater than 1. Several other types of observations also point to an exponential expansion, and unfortunately in this talk I don't have much time to go into them. I will touch on them briefly. So coming back to that first point, I'm going to break it down into the words distant galaxies and expansion. So how do we know the universe is expanding? We know that because other galaxies are moving away from the Milky Way. Some of you may be aware that the Milky Way has satellite galaxies, dwarf galaxies that, for example, the Large and Small Magellanic Clouds, and those aren't moving away from us, they're trapped in our local gravitational potential. And in fact, there's another galaxy called the Andromeda Galaxy, which is partnered with the Milky Way, and the Milky Way is actually falling into it. But other than that, all the other galaxies, billions and billions in the universe, are all moving away from the Milky Way. And how do we know they're moving away? Well, they're moving away because the further away they are, the more the colour of the light changes. And what is remarkable about the period of time we live in today as humans is we're pretty close, and I would say within the next 10 years, we will have catalogued every galaxy that exists and are observable in the universe. So if you think maybe, people don't collect postage stamps anymore, but in the old days you might collect postage stamps. Now we're collecting all the galaxies that have ever been formed, which is a really staggering thought. So anyway, there's again a lot in that, and I want to unpick it. So for now, imagine that a galaxy can be represented by an electric candle. And this picture here of this galaxy, it's called the Pinwheel Galaxy, a beautiful image that's come from the Hubble Space Telescope. And there was a lovely talk by Steve Wilkins 3 weeks ago on the Sussex Universe series about the Hubble Space Telescope. So I certainly advise you to listen to that to find out more. Okay, so we've simplified that beautiful swirling spiral galaxy as a simple candle. Now I've got a bunch of those candles, and I've put them first onto one chessboard, the one on the left, and then onto another chessboard, the one on the right. Now, it's the same candles, two different chessboards. The board on the right represents a longer time since the Big Bang. It's a bigger board. And the spaces between the candles have got bigger, but the candles have not themselves changed in size. And I think that's a concept that people do struggle with when they're first learning about cosmology. So I do have one more in my house, chessboard. It was a tiny bit small, so I couldn't quite space the candles out properly or put all of them on there. But as you can see there, the squares are much smaller. The candles haven't changed in size, but they've squashed together. Okay, so now we're getting to the point of thinking, well, how has a distant galaxy moved further away from our Milky Way, moved away faster if it's further away? And that's because the length from our chosen origin point, which is the same in both of these pictures, when you look at a galaxy that's only one hop away, it's a certain distance, but if it's 3 hops away, it's further. And the amount of time it's had to go to that size of chessboard from that little one on the right is the same, and therefore on the left, the furthest away light from our origin has travelled away faster from the origin. Okay, I know that's quite a lot to take in, but let's move on. It's very important to note that the origin doesn't matter. I didn't have any of my candles available, so I just flipped the image, but it wouldn't matter. Wherever you chose that origin, you would still have the same effect. And I think this is another point that confuses people. They assume that because the universe is expanding and we're measuring things moving faster away from us from the Milky Way, that means the Milky Way is the centre of the universe. It doesn't. You'd have exactly the same effect regardless of which candle or which galaxy you sat on. Okay, so hopefully I've explained that we know the universe is expanding because galaxies are moving away from our own. But how do we know they're moving away? We know they're moving away because the further away they are, the more the colour of their light changes. So I'm just going to play this little YouTube clip, I hope, here that's showing fire engine, and you can hear that the tone of the siren has got lower as the fire engine moved away from the observer, and it was higher as the fire engine approached. And that's the same with our candles here. They're coloured. So let's say that a galaxy has a lot of green stars in it. Green stars are quite common in the universe. Our own star, the sun, would be more of a yellow one. But anyway, let's say that it starts off as a green galaxy. As you go further away from the Milky Way, the larger the distance, the larger it's moving, the faster it's moving, the more the light is changing, and it goes through all the colours into the infrared part of the spectrum. And so these representative cartoon galaxies are not only getting smaller in size, but they're also changing in colour. So the next thing that we're going to be talking about is the fact that we're close to cataloguing every galaxy that ever exists in our observable universe, and to measure their distance, all we need to do is measure their colour. Okay. So here we are. This is that's part section of this talk. But I just thought we'll give you a little brain break. There's going to be a talk within a talk, and I'm now going to really talk about the Dark Energy Survey. Focus on that. So I put into that title in the vertical just to say that we're coming back to cataloguing every galaxy that exists. But let's just look at the Dark Energy Survey for now. And I'm just going to let you relax a little bit and watch this beautiful time-lapse video produced by a PhD student who worked on the Dark Energy Survey and was a student at the University of Cambridge. You might be able to see there the Magellanic Clouds, the large and the small Magellanic Cloud, and the very large swath of stars is, of course, the Milky Way. Here we are inside of the Blanco telescope dome. And here's the Milky Way rising behind the dome. Again, you can see the Magellanic Clouds. So thank you very much to Bjorn for sharing that. And actually one thing I didn't mention is, of course, the Blanco telescope is in Chile. Really, the Dark Energy Survey was the first of, it has broken new ground because it's the first experiment dedicated to studying dark energy, studying this crazy magic porridge pot. And if you want to do big science, you need big tech. So the top image is the camera. You can't really see the 4-meter mirror behind the camera, but to get that camera to produce pristine images, you need very large, very, very polished lenses. So this is one of the largest lenses that has ever been made. That's our primary lens in the camera. You also need a camera, and a camera is based on CCDs, like the CCDs you have on your phone, but these CCDs cost tens of thousands of dollars each, and there's about 70 of them. They're arranged in this sort of hexagon type shape. And in fact, on the bottom left, you can see an image of the small Magellanic Cloud as it would appear in the camera. The white sort of brick marks are the chip gaps in between. You can't push the electronics so close together, so you do get little gaps. And if you want to think about how large this camera is, it's one of the largest. It was at the time the largest digital camera in the world, and it still has that accolade for a little bit longer. And you could fit 4 full moons into that, so it's a huge camera. It takes lots and lots of data at once. The data it collects are like the image on the right, that sort of reddish image. You've got that long streak that is an aeroplane probably going across. You can see some individual bright stars, that very white brick shape. That's because one of the CCDs went a bit funny for a while. It's come back to life now. And then when you're lucky enough, like I have been a few times, to go to the telescope, you do actually have to look at these images to do a bit of quality control throughout the night. These you can see you've got 2 different pairs of glasses there and 2 haircuts. So that's me on 2 different trips doing my job. It can get very boring, and this is a picture of my student Sunaina after 8 hours of staring at the screen. She took a little nap. But here we are together at sunset, just before you start work. The picture in the background is one of the sunset images. You can just see the sun tucking away behind the horizon there, and there's some other pictures of me at the telescope looking very happy. Like I said, this is a job that I really, really love. I can see that I'm going to have to flip over the next slide because I wasn't expecting that one, but here we are. So when you're at the telescope, usually it is blue skies. The reason we have the many telescopes actually in Chile, is because of the beautiful weather. For those of you who like Spinal Tap, the movie, you'll be amused by the UV index that greets us when we get to the top of the mountain. It's almost always 11. But sometimes it's stormy, sometimes there's snow, sometimes there's earthquakes. It takes a really long time to build up a picture of pretty much the whole universe. And so I'm just going to show you how you take those camera images that I showed you and plonk those down in the sky over and over again over the course of several years, and eventually produce a picture of a large part of the night sky. And so here we are, going back into the main part of the talk, and I'll start that movie now. So these little hexagons are the footprints of the individual camera images. You can see that they're layering on top of each other. The layering both fills in the gaps between the chips and also provides different colours. Remember, colour is very, very important to measure the distance and speed of the galaxies, and so we have to use different filters in front of the camera to measure the colours. We also need to build up the depth. We could sit on a piece of the sky for, a long period of time, but then you'd get too many of those trails through the image. You'd get too many aeroplanes going across. You also have issues with cosmic rays, and so you have to actually take short images and then build them up over time. What we're doing now is zooming into a smaller and smaller patch of the survey, and you can start to see individual objects now. There is a false colour here, so you can start to see that there is different colours of galaxies. Here's a beautiful spiral galaxy popping out that's quite blue. There's a more distant galaxy next to it that's orange. You can see some even darker red dots, and those are the most distant galaxies we have. So thank you to my collaborators in Illinois for making that image. Okay, so we probably lost track, but we're in the section of talk which talk about supernovae in distant galaxies are fainter than they would be if the expansion was not growing exponentially. So let's talk about what a supernova is, and then talk about this thing about them being fainter. Okay, so supernova is an exploding star, and they're very bright, and they can be seen billions of light years away. This is just a little cartoon image that shows how a white dwarf is probably going to be the end state of our own sun, could go supernova. Unlike our sun, this white dwarf has a companion star. This companion star is a yellow star, normal star, but what's happening is that the white dwarf is so dense and has such a strong gravitational field, it's pulling material off its companion star, and once it's pulled off enough material, it will go bang. And if you want it, that was a cartoon. This is an actual image of a supernova. This is a picture of the Whirlpool galaxy before and after a supernova. You may not be able to spot the supernova. There it is at the end of that pink arrow. And just as a little aside, I just want to point out that that's two different spiral galaxies I've showed you, the Whirlpool galaxy and the Pinwheel galaxy. Whirlpool galaxy is nearby. It's larger, and so it wouldn't be suitable for a Hubble Space Telescope image, and even the Pinwheel galaxy took a mosaic of many images by HST to get all of its, to cover the whole thing. It's a really important point in cosmology, observational cosmology, that galaxies are similar throughout the universe. It doesn't matter they aren't exactly the same, but they have to be similar, otherwise we can't be comparing light to light when we're looking at nearby versus very far away galaxies. Anyway, that was just a little aside. Okay, so we've said that they're exploding stars and they're very bright. There's different types of supernovae, but there's one particular type of supernova, the one that results from an exploding white dwarf, that could be called standard candles. And this gives us a way to measure distance, and if you remember, that's related to speed. If you go back to thinking about the chessboard and the lights. And so here we are, here we have our candle. This time it's representing a supernova rather than a galaxy, and as it's getting further away, it's getting fainter. Now, the fact of getting smaller doesn't help in this case because the supernovae are not very extended on the sky, so they all look like points. But here's a little mock-up that I did of 2 different types of universes in my kitchen. We've got 2 rows of identical candles, and just by eye we know which one was further away because it was fainter. And then, fortunately, in a kitchen you can use tape measure to prove that that was the case. It's very important that you do have standard candles, because what happens if you have something you think is the same but actually isn't? So that would be like Mini-Me. You might think that Mini-Me was a distant supernova when in fact it was just somebody nearby who just happened to be shorter. Okay, so let's talk about this growing exponentially thing. All right, that's pretty hard. It's complex mathematics, it's supercomputer simulations, but it allows us to predict how the distance and speed would be related for different types of universes. So by different types of universes, we mean those which have more dark matter than dark energy, more dark energy than dark matter. They might have different types of geometry, they might have different types of particles, etc. I mean, what is wonderful about physics is that we can use, laws that we've developed in the laboratory and apply them to the whole universe, starting from the Big Bang and going out into the future. If you remember the video that we saw at the start, that is one particular realization of a theoretical universe. And so one of the issues we have with this whole dark energy question is that it's quite subtle. I mean, it took until the end of the last millennium, about 1999, for us to notice that there might be some dark energy, some of this exponential expansion. I mean, in this picture, the analogy is that dark matter would be winning on the left and dark energy would be winning on the right, but if you'd had a couple of beers, you might not be able to tell the difference. And so coming back to the the analogy with infections, right now we're in this slow growth pit. It's still an exponential, but it's subtle. We don't really, you hadn't really noticed it was happening. What we worry about is that at some point, it's like the R number going from 2 to 4, you're going to kick right up in terms of the rate of expansion. So, these 2 red ellipses on the curve are showing the same amount of time and yet a much more dramatic expansion in, this is in the number of infections, but, we're thinking about the volume of the universe. And so right now, we have quite, we have about 3 times as much dark energy, we think, as we do dark matter, but we don't know what's going to happen in the future. And that's why we come back to this thought of, dark energy really ripping objects in the universe apart by just making the universe expand so quickly. Okay, so coming back to our theme, supernovae in distant galaxies, fainter than they would be, I'm now going to show you some data. Now the red dots here are from the Dark Energy Survey. I'm going to explain the plot, hopefully, to you. On the vertical axis, it's the distance away from us. On the horizontal, it's the speed of recession. So remember, the further away a galaxy or a supernova in a galaxy is from us, the faster it's moving away from us, the more the colour of its light will change. Now, in the Dark Energy Survey, the supernova are really hard to spot and they don't look very pretty. So this is an example of a supernovae that's been detected in the Dark Energy Survey. On the left, you've got a galaxy with a supernova. On the right, you've got the picture of the galaxy. Because we go back to the same part of the sky over and over again, we have a picture of the before. And then right on the right, you've got what's called the difference images, showing the light from the supernovae. So these dead supernovae, they're hard to spot and they don't look pretty. By comparison, let's look at that Whirlpool galaxy. You can see the explosion and also it's embedded in a beautiful spiral system. Now going back to that plot, what we're seeing here is a clear relationship between distance and speed. And if that would, in our analogy of the light bulbs on the chessboard, That's where we've got the further away an object is, the faster away it's moving. And the fact that it's a straight line, now this is quite hard to explain, but the fact that it's a straight line between distance and speed, that also tells us we don't have a special place in the universe. I don't really have enough time to explain that properly. Okay, so let's come in for this exponential business. So what we've got, this deviation from the blue dashed curve, shows that distant supernovae are fainter than they would be if the expansion was not growing exponentially. There's an awful lot in that. So on the y-axis here, now the vertical axis, we've got the difference from expectations. And again, on the x-axis is speed of recession. The red dots are the measurements from the dark energy survey. The yellow dots are coming from another survey. And so in this analogy, this is the blue dots. The blue dashed curve would represent our dark matter-dominated universe, which is on the left, and the black dash that you can't really see very clearly, but this the horizontal line that's going through these points would be the universe on the right, dominated by dark energy. Okay, so it's been a bit of a lot to take in, but hopefully I've explained that supernovae in distant galaxies are fainter than they would be if the expansion was not growing exponentially. Now, you might say, okay, well, it was all a bit subtle, it took you a long time to figure it out. So I'll just say that there are lots of other types of observations that also point to this exponential expansion. So the plot on the left the plot on the right is a bit complicated, but just to unpick it a little bit, there are different types of observations being used to measure increasing dark matter, which is on the horizontal axis, and increasing dark energy, which is confusingly increasing downwards on the x-axis. We've talked about supernovae, so that's the green sort of banana shape that you might be able to see. Cosmic microwave background we haven't talked about. That's the blue banana that's going in the opposite direction. Then we have clusters of galaxies, which is the purple splodge in the middle. And there's also the patterns that galaxies make on the sky. That's the sort of orangey one. And the thing is, all of those are independent measurements. And this was the state of the art in 2013. So before DES had started taking data, but it hadn't started doing cosmology. And this is the state of the art that we were in. Just to give a shout out to my favourite one of these cosmological probes, clusters of galaxies. That's what I personally work in. Before that, I'll go on to saying what we got so far from DES. I've crossed out the clusters of galaxies because those results have now been published, but they are but they're in a different paper. Now, to get to this paper, there's a link there, so you can actually download it yourself if you'd like to. And in the grey splodges are showing you the results that's happened when we've combined these galaxy patterns, the gravitational lensing and the supernovae, and then we combine again with the cosmic microwave background. That's the little plots in teal. You can see that the size of those splodges gets much smaller, and the smaller the size of the splodge, the more precisely we are measuring these parameters. Okay, so we've got hopefully to the end of what's the evidence so far, and I remind you the next two bits are very short, so don't worry, should be finished soon. But before we leave the evidence so far, again, I just want to pop up a few things that perhaps you might be wondering. So in terms of the supernovae part of what I've just told you, you might be wondering why these white dwarf supernovae can be called standard candles. You might be wondering about the other types of supernovae, which I mentioned briefly. You might be wondering why, when I showed you the data from DES, the red points were from DES, but the yellow points were from somewhere else. Why can't DES do it all? And, you know, this is more a philosophical point. If you remember the curve of the infections curve, and I said we were at the point where the curve was only, you know, creeping up slowly, and, you know, is it weird that we're making a measurement today, 2020, when that curve isn't very steep? It is a bit weird. Yeah, it is a bit weird, but we can talk about that in the questions if you'd like to. Other things you might be wanting to know about the Dark Energy Survey, mentioned that the the camera's based in Chile. You might want to know more about why. When we were showing the little movie about the survey building up with the hexagonals all overlaying each other, it had a very strange shape. You might want to know why it has that shape. It might be interesting how much it cost. And certainly I'm not the only person working in DES. There's hundreds of us, so you might want to know how many people have been involved and how complicated it is. And then you might want to know why those clusters weren't included in the DES cosmology results, which is a very good question as well. Okay, so quickly, what evidence will we have soon? Okay, so DES has finished collecting data. It took about 700 nights. We were thinking it would be 500 nights, but it ended up being about 700 nights. Some of those are half nights. It took about 7 years to do. It took a really long time. Hundreds of members of the collaboration had to go to the telescope to do that quality control checking. Now, we are still crunching the numbers. We've produced results based on the first full year of data. We're very close to finishing results on the first 3 years of data, but actually the whole survey, the 6 years of data, it'll probably take about a year before that comes out. It's very complicated work. It involves a lot of those supercomputer simulations. So that's DES. So DES will improve on the results that we've got so far, but it won't really change the game. You know, it'll be dotting the I's and crossing the T's, but it's not really going to be figuring out what's going on with dark energy as a physics experiment. So we're very lucky that there'll be something else, which I call DES supersized, and it's going to be up and running very soon. And it's the Legacy Survey of Space and Time, or LSST, and it's based at the Vera Rubin Observatory. The Vera Rubin Observatory is on the companion mountain to the mountain that has the Blanco telescope, the one that has the dark energy survey. So that's on the Cerro Tololo mountain, and this one's in Saron Pachon, and you can see them from each other. It's about a 30-mile drive between them on dirt roads. Now, on the right is the artist's impression of what this Vera Rubin Observatory is going to look like. And on the left and on the right, you can see as it was just before the mountaintop shut down for the COVID-19. So, in fact, we're not far off at all. There hasn't been any work on the telescope since mid-April, but, you know, it's looking really good. It's not going to be long before we start taking data with this fantastic experiment. And what's so great about it? Well, the Dark Energy Survey has been revolutionary. I've mentioned it was the first time the experiment was designed specifically to test dark energy, but it was retrofitting an existing telescope, a telescope from the early 70s. That was done to save money. It was a 4-meter telescope. With the LSST, we've got now a mirror that's more than twice as large in diameter, more than 4 times as large in terms of collecting area. It is state of the art. Now, the next plot I'm going to show you are predictions for how LSST at the Rubin Observatory will be constraining dark energy. And first of all, I'll take you through the colours. Here, clusters of galaxies are represented in the blue, and gravitational lensing in the darker blue. Supernovae are still very important, that's in the green. The yellow is coming from a type of observation that we haven't been able to utilise in the Dark Energy Survey. It's another type of lensing, this time strong lensing, but that has a really nice way to study the distances and ages in the universe. And the red splodge is just sort of showing the state of the art that we're expecting to get from overall from things like Dark Energy Survey. So that's how things were when you combine all of their measurements, and then when you combine all of the measurements from LSST, you'll get that tiny little spot in the middle, that grey spot, and that is showing you the precision by which you can measure parameters. Now, the parameters on this curve are a bit complicated to explain. But on the y-axis, the horizontal axis, is actually telling you about physics. In the previous plots I've shown before, it's more about telling you whether the universe is accelerating expansion or not. It's not telling you why. With the LSST telescope, we should be able to figure out what the heck is going on. Why are we having this magic porridge pot universe? Okay, so it's not just LSST. There's several other experiments. I just mentioned 3 here. The Dark Energy Spectroscopic Instrument, that's already taking data. The Euclid satellite should be launched in about 10 years. Camera for that was, one of the cameras for that was built in the UK. Simon's Observatory is going to be also in Chile. It's going to be in the Atacama Desert, and that's actually studying this cosmic microwave background rather than galaxies. The other 2 experiments are studying galaxies. So there's a whole wealth of new data expected in the next decade. If any of you are at school and thinking about going to physics and astrophysics university, you can do your PhDs on these projects. There's lots more work to do. Right, so got to the 3rd point. Very quickly, the next one. Come on, there must be another explanation. Well, you know, it's a bit unfair because I'm not exactly sure what those of you out there will be wanting to know, but I'm going to say, what an explanation for what? Are you worried about the observation that distant supernovae are too faint? Or are you worried about the inference that dark energy is driving the expansion? So I'll just break those down. If it was a case that those distant supernovae were too faint because they weren't exactly standard candles, that could certainly be a case. Then you could say, well, actually, it's not because the universe has got an exponential expansion, it's just because distant supernovae, they've had less time to evolve since the start of the universe, and so they just are different. So it's a bit like the mini-me versus Dr. Evil. Yes, that could be an explanation for that curve that I showed you from the Dark Energy Survey supernova results, but it wouldn't explain why we're also getting the same inference from all those other observations, from the weak lensing, from the galaxy patterns, from the clusters of galaxies, from the cosmic microwave background. It's just, if there was only one line of evidence, you could suggest that perhaps the universe wasn't expanding exponentially. Unfortunately, there are many. Okay, so then you could say, well, okay, but you've talked about dark energy, you've never really said what it is. I just hinted that perhaps with LSST we might understand the physics of dark energy. Could it be something else that's driving this accelerated expansion? Well, it could be. And in fact, dark energy is a catch-all term. We don't really know what it is. The most attractive suggestion would be that it is something called cosmological constant, was actually predicted by Einstein, and it is something that we would expect to be associated with increasing volume. The more empty space there is, there's more something called vacuum energy. But if that was the case, there's all sorts of other questions that just don't make sense. There's a mismatch between different branches of physics. So there's a hope that perhaps the dark energy isn't a cosmological constant. Key thing not being a constant, that it changes with time. If it changes with time, maybe it was low. It's sort of in the last couple of billion years, it's grown up. And then rather than us going into this big runaway expansion, it goes down again. That would be useful. Another explanation would be that perhaps we are putting the wrong physics into those supercomputer and mathematical calculations. We assume that the gravity that Einstein derived, general theory of relativity, would does work, not only in our own solar system. It's been proved to work extremely well in our own galaxy, but we assume it works everywhere on the universe at all possible scales. Perhaps it doesn't. This accelerated expansion could be explained by gravity getting weaker as objects get further away. Unfortunately, gravity getting weaker still has an accelerated expansion, and so we still end up with doom. So sorry about that, but yeah, there may be another explanation, but I'm not really sure that it helps, except for, I do not want you to panic. There are, detailed models of how we might go from the expansion that we're in right now, which is sort of a controlled expansion. It's still an exponential expansion, but it's a controlled one. and the prediction is that runaway part, the part that's going to rip the solar system apart, won't really happen for tens of billions of years. And so, quite frankly, you've got other things to worry about. Anyway, I'm just going to draw that to a close now. We'll be moving over to the Zoom session if you're watching this on May 14th, 2020. And you can ask questions about any of the things that we've covered related to dark energy destroying the universe. So dark energy destructive potential, the evidence that we have for it so far, the evidence that will come soon, and come on, there must be another explanation. So thank you very much for your attention, and I'll stop there. Thanks now.
Well, we hope you enjoyed this video. Once again, I've got to ask, if you did enjoy it, please give the video a like and subscribe to our channel to see our future updates. If you're interested in the future talks we've got coming up, do visit our website at bit.ly/SussexUniverse. And remember, if you're watching live, the live Q&A starts now at the Zoom link in the description down below.